Welcome to my new calculus channel. My name is John Gabriel. For decades, the mean value theorem has been stated as a non-remarkable theorem by the mainstream academia. And the way it has been stated is in this particular form here. There exists a C such that the derivative at C is equal to this particular ratio here, where what you have over here is a curve which is f dash of x, or the derivative of x, and somewhere along here there is a tangent line, and that particular length there is actually the arithmetic mean of all these infinitely many ordinates. Now that's not how it's stated in the mean value theorem. The emphasis is placed on the existence of a C in that particular interval, in the interval a, b. Now let's think about this. Supposing you have any particular curve. Let's take this particular curve here, right? Over the interval AB. So let's go like that, and do that, and do that, right? So now, even inside here, there is a C, which is the arithmetic mean of all these ordinates. Okay? So the difference, though, between this particular scenario, this scenario here, and this scenario here, is that what you have here is a natural average, which is a result of this function here being not only continuous, this one's also continuous, by the way, but smooth. Okay? So this function is also smooth. What does it mean for a function to be smooth? It means that at every point in this interval, only one tangent line can be constructed. Okay? So you can only have one tangent line at every point in the interval. That's what makes the function smooth. That is the definition of smoothness. In this particular function here, you can have many tangents, okay? So while this is continuous, it's not smooth. And so in this case here, there is a primitive function. But in this case here, there may not be a primitive function. However, there is still an arithmetic mean. Okay? So if this function here is called f dash x, then f dash c exists. Somewhere along here, one of these y ordinates, or at least one of these ordinates, or y values, will be the arithmetic mean. Okay? So, there is nothing really special about this c, because there'll always be an arithmetic mean. It's pretty obvious that if you have an interval and you have function values in an interval all defined, in other words, they're both continuous, so all you need to have an arithmetic mean, all you need for an arithmetic mean is for the function to be continuous. Okay, so, and in both cases they're continuous, so you have an arithmetic mean. Now, how do we use this information here in calculus? Well, the fact that the derivative at C is related to this ratio here is a result of the function being continuous and smooth. Okay? So, when we look at this, we'll see that it's not so important that there's actually a C but rather that there is an arithmetic mean. Okay? So the arithmetic mean is what's important. And why is the arithmetic mean so important? Well, let's see why. First of all, one of the facts that most academics have not realized is that this area here under the curve of the smooth and continuous function, or continuous and smooth function rather, is a product of two arithmetic means. It's a product of this arithmetic mean and the interval width. To see how that works more or less, let's look at this applet here, and we'll see that this blue line here is the arithmetic mean of all the y ordinates in this interval. So I can move this along like that, and each time you'll see that it shows me the arithmetic mean, right? To find this entire gray area, all I need to do is find the arithmetic mean and multiply it by the interval width, which is the pink line, right? So the product of this ordinate, the length of this ordinate and the interval, will give me the area, the gray area under the curve. Incidentally, the gray area under the curve is equal to the yellow shaded area in both cases. Okay? So this here gives you an example. If I have to do this and move it up and down, it shows you that the whole gray area here is equal to the yellow area when we move this gray area down to this spot here. And similarly, what's happening is that we're simply using a process called quadrature to move this gray area into a quadrilateral, okay? And that way we find the area of the curve between the curve and the x-axis and these ordinates. And so really what we have here is a product of two arithmetic means, okay? So let's go back to this diagram here. In other words, what is the original definition of area? If you have a rectangle like that, and you find the arithmetic mean of all the vertical lines inside here, all the vertical lines, the length of all the vertical lines, that arithmetic mean will always just be the height, yes? Similarly, if you take the arithmetic mean of all the innumerably many horizontal lines, then you'll have the length. And of course, the height times the length gives us the area. And this is exactly what's happening in calculus with the mean value theorem. The mean value theorem is telling us what the length of this arithmetic mean is, which is in effect helping us to perform quadrature. So we're performing quadrature here. We're moving this whole entire area here into this quad. Okay. Similarly, that's what was happening in the original definition. That's what is happening in the original definition of area where a quad is concerned. So area can be defined as the product of two averages. The interval width, which is the average of all the horizontal line lengths, and the arithmetic mean, which is the value, it's the value of the ordinate that is the mean of all the lengths of the ordinates in this interval. Does that make sense? Okay, so you can look at this particular video again and study it in more detail, but I'm going to carry on and see how much more I can tell you to make this clearer. So we've looked at that diagram. Now we can look at the definition of the mean value theorem in terms of the mainstream calculus or the new calculus. In the new calculus, it's well defined, but it's also possible to do it in the new calculus with the aid of something that I discovered, or I invented rather, many years ago. It's called the positional derivative. So I define a derivative as you see in this document here. And I use that to prove that the left-hand side, f dash of c, is actually going to reduce to the quotient that you see so often described as the mean value theorem. So that last statement there is a direct proof of taking the supposition that the mean value is the arithmetic mean of all the ordinates in a particular interval. In other words, this sigma sign that you see here gives you the arithmetic mean. And this is the way you would do it using the bogus mainstream calculus. If you would like to see how this is done in the new calculus, then you'd look at this article here, okay, which is much simpler. It's only a page, has no limits, based on the new calculus derivative definition, and it uses a proper mean. As you see, those mu's down there are actually the arithmetic means. And the proof of that in the new calculus is similar but not quite the same. On the left-hand side there, you will see 1 divided by k, and the sum from s equals 1 to k of f dash mu sub s. And that will give you the mean value theorem. And if you go through the proof, you'll end up with the ratio stated as a derivative, and it's equal to f dash of c, which is what you wanted in the first place. And the final line in the article shows you how the fundamental theorem is derived in one step from the mean value theorem in calculus. So if I've said all that correctly and I haven't made too many mistakes, this is an impromptu video, by the way, so if I have, well, you can make a comment later and we'll talk about it. But this is really the correct statement of the mean value theorem. The one that you see over here is the correct statement. So let's just pull it up here. This here is the correct statement. This is the correct statement of the mean value theorem. And this here is equal to this here. It's equal to that, which reduces to what you see over here in this diagram, in this article, in the mainstream article, which reduces to that. So this here is the same as that. Okay? As you can see, the new calculus definition doesn't use limits. It's much simpler, it's resilient, there are no flaws, and it works perfectly every time. Okay. Before I finish this presentation up, I'd just like to say that until I came along, no one actually understood that area is a product of two arithmetic means. And I don't think anybody even understands that volume is a product of three arithmetic means. So, for example, in calculus, when you calculate the volume of solids, you're actually finding the product of three arithmetic means. And so that's a better way of defining volume, and this here is a better way of defining area. And it describes exactly the method of quadrature and cubature. Quadrature meaning to find area, and cubature to find volume. And of course, if you're looking at hypervolumes, then you're looking at dimensions greater than 3. Now, the new calculus has facilities and new features to handle all these things with some powerful new theorems and new properties. The first thing you'll notice when you begin studying the new calculus is something called the auxiliary equation. It's a very powerful feature of the new calculus, which is not possible using Newton's bogus calculus. The auxiliary equation can be used for many different things, and you'll find a whole list of them at my website. the one which is called the new calculus.weebly.com. And if you go to the new calculus course page at that site, you will see the many uses of the auxiliary equation. Okay? So now, this particular statement of the mean value theorem actually says that if you take the arithmetic mean of all these ordinates of f dash of x, then it'll be equal to this quotient here, where f dash of x is related to its primitive f of x. And that's what the mean value theorem actually says. In addition to that, you can also watch some of my videos, and one of them that deals with that particular subject in detail is the one called Academic Ignorance and Stupidity Part 16. So if you go to this video here and you double click on it, and this video here now explains everything I've explained to you now, and perhaps in a little more detail, so that you can understand it better. Well, that's pretty much it then. You can find a lot more on my YouTube channel, a lot more hot topics in mathematics. And in addition to the much acclaimed Academic Ignorance and Stupidity series, you'll find lots of other videos discussing topics that are controversial or not clear in mathematics, and also some new concepts and methods. And of course, there's also a playlist with the new calculus videos to get you started very quickly. Well, that's pretty much it right now. I think I have covered everything. I will put links to all these applets and articles in the details section of the video when I upload it, so that you can access them, as well as the links to my Google Drive and the YouTube channel. This has been a presentation on the mean value theorem, stated correctly for the first time in human history. I am John Gabriel, and I hope you enjoyed the presentation. Till next time, goodbye.